Hello everyone, my name is Harnit, Assistant Professor in Ajay Kumar Garg Engineering College. Yes, we were doing predicate and proposition and predicate logic. In first video, we covered all the symbols in it, what the properties in this. In this, we will be studying about the arguments and the inference rules. Right? This is second part of this chapter. Right? What is an argument? It is an assertion that a given set of propositions P1, P2 up to Pn called premises yields has a consequence. Another proposition Q called a conclusion is denoted by this symbol, right? P1, P2, Pn up in conclusion is Q, right? Valid argument. An argument P1, P2 up to Pn, the symbol should be here, and the conclusion Q is said to be valid if Q is true whenever all the premises are true. That means the premises given in the question, right, should be true for a conclusion to be true, right? What is a falsy? It is an argument which is not valid. Now, P1 up to Pn are true simultaneously if and only if the proposition P1 and P2 up to Pn is true. Hence, we have the following theorem, right? The argument P1 up to Pn, conclusion Q, is valid if and only if Q is true whenever P1 and P2 and up to Pn is true. And this up to conclusion is a tautology, right? The meaning of this theorem is that whatever premises are given, right, we have to AND all the premises. AND operation should be performed. And after performing the AND operation, our ultimate output should be true, right? This means that the given premises and the given argument is true, right? Now, procedure to prove the validity of an argument. How will you proceed? How will you check whether this argument is true or not? The conclusion Q is said to logically follow from the given premises P1 to Pn if either of the following condition is satisfied. Q is true whenever all the premises are simultaneously true. Q is what? Conclusion. Conclusion is true when all these premises are true, right? Some premises P1, P2 up to Pn, and this is the conclusion. We should have true in all the parts of this row, right? Where all premises are true, the Q has to be true there, right? If one of the premises are false, suppose, right? And this are true, here should be false, right? Q is true whenever the conjunction means and of all the premises is true. P1 and P2 and up to Pn, that is, implies Q is a tautology. All the three statements have the same meaning here. Now let's check. P implies P or Q. This is also the symbol for that, right? Is where we have to check whether it is true or not, whether it is valid or not. How will we be doing? We will make a truth table. P and Q, we can see the premise that only two literals are being used, P and Q. We can take the input values for P and Q. We will calculate P or Q, right? Now the premises are P, and the conclusion is P and Q. We have to check that when premises are true, here we have to check this row, we have to check this row, right? Because premises are true in this row only. And the conclusion is P and Q. These conclusion in this row, conclusion in this row should also be true, which is true. That means this is a valid argument. P is true in row 3 and 4, in which P or Q is also true. Therefore, P implies P or Q. Now, show that let's take this example now. Show that P double implies minus Q does not logically implies P implies Q. Now we have to prove that this is not a valid argument. How will we be proving that? Again, we can see that there are two literals, P and Q. We will take P and Q. We will take the inputs for P and Q. And we also require minus Q. We will calculate here minus Q. Then we require P double implies minus Q. We will calculate here. And then we require this, right? Now we have to check the premises. Premise is this one only. P double implies minus Q. P double implies minus Q. True is here. It is true here. So we have to check only these two rows. The output should be high for both. For this it is high, for this it is low, right? So that means it is invalid. It should be high here also for validity, right? P double implies minus Q is true in row 3, but P implies Q is false. Therefore, P in double implies minus Q does not logically implies P implies Q. Limitation of propositional logic. What we have studied till now, it has some limitations also. The facts that Peter is a man, Paul is a man, John is a man can be symbolized by P, Q, R respectively in propositional logic. But it cannot draw any conclusions about the similarities between P, Q and R. All the three statements have a similarity that Peter, Paul and John are men, right? So, better to represent these facts as man can be Peter, man can be Paul, man can be John, right? Even more difficult to represent sentences like all men are mortal. Now, this is the more generalized statement where the whole population is included in this proposition, right? All men are mortal, right? Now, such sentences really need quantification. So, what we'll do, predicate logic is introduced for such type of statements. In predicate logic, these limitations are removed to great extent. Predicate logic is logical extension of propositional logic. First order predicate logic is one where the quantification is over simple variables, right? Propositional logic is limited. For example, how we express all math undergrads are clever in terms of cleverness of particular maths undergrads, or express there is a math undergrad wearing sandals in terms of whether each individual math undergrad is wearing sandals. So this type of clarity is not possible in proposition. We therefore generalize the idea of proposition to a predicate. Predicate takes one or more variables or as arguments, right? In predicates, it is not a full sentence. Only a part of sentence we will take in the predicate. Rest of the sentence we will be defining with the help of variables. Like, see here. Px be the statement x is greater than 12, then P1 is false. Now, x is greater than 12 is a generalized statement. X can be anything, right? The whole population is included now, right? All the numbers are included here. We can check that particular predicate for a particular number. Since see here, we are checking for 1. For 1 it is false, but for 13 it is true. For 15 it is true. So predicate can be true or false, right? Like see here, P1, for P1 it is false and for P23 it is true, right? Predicate can be true or false at the same time, just the value depends on the variable we are taking. Let Px denote the statement X is a faculty of MCA department, then P, suppose Dheeraj is in MCA and Akash is in applied science or some other department, right? Then for this statement, P Dheeraj is true and P Akash will be false, right? Thus, Px is not true or false until we specify the argument. So, most important thing is we have to specify this. argument here. Universal quantifiers, those which refer to all the elements of certain set, for example, all, any, every, each, none, no. The universal quantification of Px is the preposition Px is true for all the values of x in the universe or discourse. It can be denoted with the symbol this one. This for all, where we have to symbolize that the particular predicate is true for the whole population, then we have symbolized with this symbol, right, which we read as for all x or for every x, for all x or for every x. Suppose Px is a predicate, x square is greater than equal to 0. Then we can say that for all x belonging to R, Px, that is for all real numbers, x Px, right? For all real numbers, x square is greater than or equal to 0. We want to represent this sentence with, we can say this. This way is to represent for all x belonging to R, Px. And what is Px? Px is x square is greater than 0. Px, x square is greater than equal to 0. Right? Existential quantifier, the existential quantification of Px is a proposition there exists an element x in the universe of discourse such that Px is true. It is denoted by there exists. The there exists symbol is like this. It means that it is not true for the whole population. Only some part of the population is included in this. Either it is one, it can be one person, or it can be a group of person, but not the whole population. Which we read as exist x such that Px. Now there exists x belonging to positive integers such that x square is equal to x. Right? Now x square is equal to x is true for some part of the population only, not all the positive integers. Only some integers like 1 and 0 will come here, right? Not all the numbers. Prepositional function. A prepositional function or a predicate in a variable x is sentence Px involving x. That becomes a preposition when we give x a definite value from the set of values AKGEC. Such functions are denoted by Px or Qx. The set of values x can take is called universe of discourse. Example 1, every flower is red, right? Now for all x, if x is a flower, then x is red, right? Every flower is red. For this statement to be true, first the x should be a flower. And if it is flower, then it should be red in color, right? So Ax, we will divide this predicate like this. Ax is x is a flower and Rx is x is red, right? For all x, if Ax, if it is a flower, then it is red in color, right? Now let's discuss the other example. An integer is either positive or negative, right? We can write it like this for all x. If x is an integer, then it is either positive or negative. Now symbolically we can write Ix is equal to x is an integer. Px, x is either positive or negative. For all x is an integer, then it can be either positive or negative. X is the father of mother of y, right? Now understand the sentence. X is the father of mother of y. First y is there, then his mother, and then his father x, right? So how do we represent? If x is a person, right? Then we have two things now, x and y. First function is f. F is the father of y. X is the father of y. Now x is the mother of y. X is the mother of y, right? Now, we name a person called Z. Suppose this predicate or this sentence is true for Z, right? Z. From the whole population, it is true for Z only, right? Then Z as the mother of Y. Now we want to say that X is the father of Z and Z is the mother of Y, which symbolizes there exists X, Z, where Px, what is Px? Z is a person, right? If we substitute Z here, that means Z is a person. And X is the father of Z, right? And Z is the mother of Y. This way the representation can be done. Now the statement is all animals are dogs. Now we want to negate this statement. Okay? All animals are dogs. That means all the animals means we have to put the all symbol here. All X belonging to A. X is a dog, where A represents the set of animals. Negation of statement. It is not the case that the animals are dogs. Just we will put a negation sign in front of this. Right? But we can also write there exists at least one animal who is not a dog. Out of the whole population, if one thing is false, then it is false for the whole, it becomes for all to there exist, right? Because if it is true for the whole population, then only we can use a for all symbol. But if one thing is false, then we have to use a there exists symbol, because now it is not true for the whole population. There exists X for A when X is not a dog, right? Means for all symbol will be converted to there exists symbol when we are negating the statement. Now we come to inference theory. Sorry. Inference theory is a concern with inferring of conclusion from certain hypotheses or basic assumption called premises by applying certain principles of reasoning called rules of inference. The following 6 rules of inferences are law of detachment or modus ponens. The same meaning is there. Law of contraposition or modus tollens. Hypothetical syllogism, disjunctive syllogism, conjunctive dilemma, and destructive dilemma. These are the symbolic forms of all these laws. Law of detachment, if P implies Q and P is also true, then Q is also true. If P implies Q and Q is false, then P has also to be false. This is modus tollens. Hypothetical syllogism says P implies Q and Q implies R, then P implies R, right? Disjunctive syllogism says if P or Q and negation of P, right? This is true, but P is false, then Q has to be true. This says disjunctive syllogism. P implies Q is true and R implies S is also true, then P in or Q, right? P or Q, then Q and S. Q or S, right? If these 3 terms are true, then Q or S will also be true. Destructive dilemma, P implies Q, R implies S, negation of Q or negation of S implies negation of P or negation of R. This is destructive dilemma. Now let's take one example of law of detachment, modus ponens. If P implies Q and P implies Q. Suppose P is Mohan can work hard. Q is he will get a job. Premise is P implies Q and P. Conclusion is Q. Q is, now this is the first premise. If Mohan can work hard, then he will get a job. Means P implies Q, right? And this Q is he will get a job. right? Therefore, he gets a job, right? This is the conclusion, right? You can directly apply this modus ponens here, law of detachment. You are not to prove this law because it is a fixed one, it is already proved one, right? Just you can apply on the questions like this. Modus tollens, right? Test the validity if the following argument. If Rams work hard, he will get the job. Ram works hard. Therefore means this is a conclusion, right? Therefore, he will get a job. Now, let P denote Ram works hard and Q denote Ram will get a job, right? The argument can be written in this form. P implies Q. If Ram works hard, he will get a job. P implies Q. Ram's work hard is P, right? Now, the conclusion is Q, right? This is for example. Here is the premises are P implies Q and Q, the conclusion is Q. We have applied law of detachment here, right?